Thanks very much indeed, everybody. It's a great privilege and a pleasure to be here in this beautiful location to speak at POPL 2019. And I want to just thank the many people who financially and, more importantly, intellectually, who've supported this work, not least my co-author, Garrett Morris, in the front there. I want to start by stealing something from Frank Fenning and his lovely mentoring workshop talk, in which he identified, excuse me, that one of the things we seek to do as POPL people is to identify the simplest and most elegant abstractions to capture phenomena of interest. But I also want to thank the reviewers of a number of conferences from which this paper was first rejected until finally accepted at POPL, who also draw attention to the fact that, in particular me, a holy fool, had wandered into a garden of delights. And I think this was meant as some kind of warning about what it was we were engaged with. So let's focus in on the phenomenon, namely of extensibility. And I'm sure that sets off all kinds of light bulbs in people's heads. So let me say that again, as POPL people, we're already going to slightly bias the focus on the problem by saying that we want to capture the phenomenon of extensibility through type systems, and in particular through the idea of inclusion or subtyping in type systems. And the idea of extensibility cashes out in a number of ways and in a number of different proposals for type systems. I'm going to narrow in on Mitch Wan's work on record types being used for inheritance in OO, but of course the modern interest in session types, also in contemporary theories of effect types and handlers, as well as the classical, now perhaps infamous problem, infamous not because it has Phil's name attached to it, of the expression problem in data types, that this phenomenon occurs widely, and we would like a uniform account that captures all of these things. Let me just signposting something that will hopefully come later, just to say that all of these problems attract a kind of conjunctive disjunctive duality reflected in producer-consumer behavior and also in the type theoretic sense in terms of products and sums. So for those that are not familiar with rows, and in particular this 30-plus year field of study, let's go back 30-plus years to Mitch Wan's LIX 87 paper, where he introduced rows and reminds us that in fact they've been here even longer, namely 50-plus years, from the Algol 68 report. And there, rows are essentially finite mappings from a countable label set to a set of types that we can then reify as types either as records by applying pi to them, or as data types, the familiar data or data type of Haskell or ML, by applying sigma to them. Each of those flavors of rows, or rather their reifications, come with introduction and elimination operators. I won't say much about them, they're familiar or not, but they come with interesting typing problems. And just to fix familiarity with these things, just to draw attention to the fact that for the singleton set of tau labeled with L, the pi row, the pi type associated with the singleton row, and the sigma type associated with the singleton row are obviously isomorphic to the underlying type tau, essentially by labeling and unlabeling. And that's essentially the content of Haskell's new type. Now, they were introduced as an attempt to capture extensibility. And again, I'm going to focus on one subsequent paper on multiple inheritance in OO, which focused on the problem of giving principal types to, well, a complex operation. It first concatenates two records that corresponds to amalgamation of fields coming from two distinct classes in an inheritance hierarchy, and then projecting out a field with label L. And the search is for a principal type for this operation. And the conclusion of his paper is rather negative. It says it's not possible within a simple enough typing system to offer principal types for that operation. So subsequently, Didier, with the extension of the usual Hindley-Milner with presence and absence annotations and polymorphism over those annotations, was able to give a nice type theoretic account of record extension and update. So those are somehow conjunctive problems because they're about products, but also there are corresponding problems and solutions associated with the disjunctive side of the story. And I just want to mention Wouters Veerstra's a la carte approach to data types. that's essentially driven by inclusions between coproducts of functors describing data type shapes. But that also comes at the term level with some syntax, which we've already seen in a couple of talks about algebraic effects at Popple, essentially through Benton and Keddy exceptional syntax that was subsequently rediscovered and reinvented by Patrick Barr, looking at a la carte inclusions with type families in Haskell, and Garrett Morris in his variants on variations, or variations on variants. So what's the real problem? The real problem is how to type these phenomena. So taking Leslie Lamport's precept that you shouldn't experimentally bias yourself, although notice I've already done so by saying I'm going to give a type theoretic account of extensibility, is that you should state the problem before you announce your solution, just to allow the reader the illusion that there really is some independent experiment taking place here. And so we can articulate a problem of typing extensibility as the search for a general enough theory of row types, and their applications obviously, that has the usual trinity of syntax, semantics, and pragmatics in the following sense. First of all, we want to capture row type theories of interest, but also crucially that the primitives should somehow be simple or intelligible enough in their typings that we can actually use them in practice. There's no point in introducing a type system so complicated that we don't actually know how to use it to do simple things. But also we want a semantics derived from the metatheoretic properties of that type system, which has good behavior. And in particular, Wand was searching for principality, and I'll come back to that issue as a consequence of our choices later. And then as a bonus, for someone who was educated in the Milner-Harper-Tofter school of explanation of high-level languages by elaboration into simpler ones, it's a bonus if we can piggyback on something simpler to get the meta theory, well, not quite for free, but somehow the advantage of theft over honest toil. So we introduced a language in the paper, and we call it rows, rather playfully. And what is the essence of rows? The attar of roses is the idea of row concatenation as a thing in itself, an operation on rows, not on types. And the crucial thing is that this be a partial operation and also a monoidal operation. And I'll come back to the consequences of that in a minute. So if we look at what we'd like to write, or indeed what Wand would wish to have written, it's that if I have two input rows, two pi rows, and I somehow want to, they're records. So if I concatenate them, what am I going to get? I'm going to get a record. I'm going to have something which is pi. And what will that be pi of? Well, I need a notation for the underlying row that explains the record structure. So let's posit the existence of an operation that describes that. But that's really an abuse of notation, because what we really understand is that if we're given two input rows, we can construct another record, two pi rows, two records, we can construct a resulting record only provided that the three instances of rows actually participate in a three-place relation, which is essentially saying that this hypothesized operation is actually well defined. And I've used the simic, the twiddle, to say that there's probably some kind of equivalence relation going on in the background there. But the thing to note already, and in some sense, this is most of the way to the last box, which is finally a solution to Wand's problem, is a principal type. This is for record concatenation, given by delegating to the only reasonable thing it could be, namely an underlying concatenation operation on rows themselves. And then with that, we can now type the multiple inheritance construction as follows. Provided the labeled type tau with label L actually occurs as a sub-row of the composite, then given two input rows that we have hypothesized as put together with O dot, then I can indeed construct a value of type tau. So what's the overall picture of the solution that I'm going to describe in the rest of the talk, and that is laid out in detail in the paper, is somehow a theory of row theories, and indeed an account of how those will be dealt with in compilation and the runtime system to actually explain their behavior. So rows as we see them now in our language rows, well, labeling and unlabeling, they're not so surprising. And concatenation, I'm making free use of the abusive notation here, and that's used throughout the paper once we've explained it. I'm just going to consider the pi fragment because the sigma fragment is literally given by dual operations. We have a general notion of projection. And this is worth focusing on for a minute because, again, it uses this idea of inclusion that was already lurking in the background of the Spherestra a la carte analysis. And what does it say? I can go from a wide row rho to a narrow row rho L, provided, again, always on the assumption to the left of the implication arrow, that the rows stand in an inclusion relation. Well, that sounds extra complexity. I've already said we need concatenation. What about this inclusion operation? Well, this is one reason to need a monoidal operation because it's a standard thing in category theory that, well, or even in the theory of monoids, that it induces a partial order, pre-order, let's not split hairs, on rows given by existentially quantifying over the monoid. So in fact, this is a defined notion, and it will always be explained definitionally in terms of the three-place relation. Now, having done that, we can go back to the simple theory of rows in WAND 87 or Algol 68, and say field lookup is just a composition of a projection first in order to narrow down to the singleton row, followed by delabeling. And so again, it has a principal type which takes a pi row and will project out a value of type tau so long as the labeled field actually occurs in the row. And similarly, we can give a definitional account of WAND-RAMI update and extension with a uniform typing, so there's a twist there, by inserting a combination of projection and concatenation. Now, the type and the explanation of why we have a principal type for that, you'll have to see the paper for the details. So how on earth does all this work? Well, rows is given by specifying a notion of row theory, and in some sense it's the obvious thing. It's the syntax and the operations of monoidal concatenation and a notion of equivalence relation on rows, together with, well, we're working in Jones-style qualified type, so I need to be able to explain the semantics of predicates. So I'm also going to need to explain a notion of entailment between predicates in order to consider eventually in the type system satisfaction of predicate instances. That's a notion of a row theory. There's a notion of algebra for that theory, and it's exactly what you think it ought to be, namely a partial monoid. Now, one reason to have algebras for the theories is precisely to provide a computational interpretation of the syntax of predicates, and we'll see that later in the translation of rows to a core language. And then the only thing to observe is in exactly the same way as type classes in Haskell dispatch at a call site on a particular dictionary for looking up the operations, all the primitives are parametric in a given row theory. So actually, in any given rows program, we can imagine instantiating all the uses with possibly multiple row theories, and that's something I want to go on to describe. I said that we wanted a bonus feature of the solution to the problem, and I won't say much more about it, except to say it has an entirely standard translation into a simple extension of system F with, well, you can imagine what it would be, is n-ary products and sums. Why would that be? Well, labels are a countable decidable set, and in some sense, n is already a good enough exemplar of that notion, and indeed that's how we translate labels away. So the thing to remark is that in some sense the meta theory of rows comes for free by delegation to F plus times, but also that the idea of labels are not intrinsic to row typing. They're just a surface notion which is explained away in the translation. So there are examples in the paper, and of course you might expect that the first and simplest example is exactly the WAND Algol 68 RAMI Wadler row system, as we saw it already. That's just finite sets of labeled types with disjoint label sets. And the disjointness helps in the analysis of extension and update. But much more interesting, and in some sense this was the spur that the reviewers gave us, was to consider other row theories. We were already interested through our collaborations in Edinburgh with people working on effect typing to consider Dan Lyon's very influential scoped row theory and its use for providing scoping of effects. And that gives rise to a very nice, because interesting, row theory, namely a non-commutative one. So the idea that successive occurrences of a labeled type in a row can shadow in order to enforce effect scoping actually arises as concatenation being a non-commutative operation. And we can further consider operations that put row theories together. So again, thanks to the referees, our attention was drawn to an early paper by Mackham and Wells about modules and mix-ins, where essentially we play a game of having co- and contravariant pairs of rows corresponding to input-output interfaces to modules. And then my observation that rows is parameterized at the call site level by row theories means that one language can accommodate all three modes of use. And then as far as the semantics goes, well, there's something to say about row algebras, and we're able to, through not much work, read off principality and coherence for rows from the underlying properties of system F. Now, how might we evaluate this? It's no point in doing an experiment positing a problem and its solution without some kind of evaluation criterion. And Lamport reminded us not to cheat. So I'm not going to cheat. I'm going to take 3 lessons from Frank's talk about desiderata for a type system and explaining a problem. And I particularly want to draw attention to the last one, that type systems should give a new way to think about programs. And I think it's this extension that we're able to capture non-simple row theories that allows us to bring other phenomena of extensibility under one roof. Now, it's not just Frank's criteria. I also want to now go back to the reviewers again and say, yes, that warning, well, now that comes back to us because, okay, an earlier version that was rejected reminded us that it's nice to have a unifying account of a large number of papers. And one thing I'd like to say about rows in summary is that it's been an adventure for the last 30+ years, but like so many things in science, it would be nice now to draw a line under that era and say that we have a new, simple, uniform, and hopefully elegant basis to undertake a new era of research starting from rows. Now, that's not quite my last word. There's plenty of future work to do, and in particular, all the people who gave talks about effect systems and the problems of scoping and leaky abstraction, I hope we can talk to them about those features offline. Thanks very much indeed.
So once again, if you have a question, you're welcome to enter it into Slido, and I'll ask the question from there. Else, please raise your hand, and we'll bring the microphone to you. I'll do the first question from Slido. Can you elaborate on the properties that you get for free that you mentioned a bit earlier?
So principality, we essentially want to compute a unique type for which every rows program that is well typed is an instance of its principal type. And coherence is usually a problem in complex type systems that we want somehow typing to be independent of a typing derivation. And with a certain amount of work that I'm grateful that Garrett did, we were able to obtain coherence for the theory. So that's just a little bit of extra detail there. I hope that's a sufficient answer. Benjamin?
Great talk.
Oop.
It's on. Go ahead.
Great talk. What about subtyping?
It's unusual to find myself lost for words. You know that I'm a blabbermouth. I would say that rather in the spirit of Bill Cook's Popple 1990, inheritance is not subtyping, I would rather understand this by saying, let's not think about subtyping, let's think about row inclusion. But actually, I know that you're far too sophisticated a thinker in the arena of subtyping to let that one go just like that. So definitely let's talk about that offline. Thanks very much, Benjamin.
Thanks. So is there a certain amount of choice in how you do concatenation? So say you wanted something that started, if you had two labels at different times.
Let me stop you right there and just say, exactly, it's in your hands as a language designer to stipulate the particular row theory in which you work.
Okay.
And in some sense, that's the only solution we could have given to one's problem, is to delegate the meaning of row concatenation to the task at hand. And that's why, yes, render unto Mitch that which is Mitch's, or in this case, to Dominic. Didier, Claudio, Phil?
I'm afraid we
We're
have
out of
time.
time.
We're out of time.
Huh.
We have time for one more question.
Didier. Come on, Phil, I used to work for you. You can talk to me anytime. Yeah.
So you're showing several examples that could be encoded into this framework.
Yes.
But the scope rows that you mentioned here, they are actually a subcase of simple rows. So my question is whether there are other examples than simple rows that you have tried in this system.
So, I think for us, rightly or wrongly, it was an important insight to identify non-monoidal row theories. Non-commutative monoidal row theories. And it's in the paper that a feature that indeed the layering of successive scope of effects gives rise to a non-symmetric operation. Whereas for simple rows, when you have disjoint label sets, exactly that doesn't present a problem and the theory is symmetric. So I think actually there is a bit more subtlety to successive appeals to the same label. But let's look at the details offline. Thanks.
Thank you again. Let's thank our